Hi everyone. Last time we discussed about implicit partial differentiation, and this was our last example. We tried to use this concept to find the partial derivative of the given function of two or more variables. Now using partial differentiation, and we're able to find the slope of the given line that is tangent to a certain point. In this example, we're given a sphere and we have two line here, slope of the line that is at the upper hemisphere, which in our calculation we get the negative result. Again, we have here, because this is sloping downward to the right, so naturally uh, from the previous concept, so this is a negative slope. And this one here for the lower hemisphere, so we have here the positive slope because this is sloping upward to the right, so we got here a positive value. Okay, so one more example for this topic. But before we go to the next example, we can also try to verify our answer if you're going to check our answer using this, right? Instead of doing it or differentiating it implicitly, you can also do it in another way, expressing z as a function of x and y, but this is in radical form, and for sure you will get the same result. I will not do that anymore here. So for your practice, you may verify our previous answer um, using this equation and then take the derivative of this function with respect to x and y, holding the other variable as constants. Okay, so please kindly verify our answer using another way of doing it. Now, our next example is this one, example number 8. Suppose that we're given here a function d equal to the square root of x squared plus y squared, which is the length of the diagonal of a rectangle whose sides have length x and y that are allowed to vary. Find a formula for the rate of change of d with respect to x if x varies with y held constant or fixed, and use this formula to find the rate of change of d with respect to x at the point where x equal to 3 and y is equal to 4. Okay, so for our solution, so differentiating both sides of the equation implicitly, right? So we just transform it to what we did here. We just take the square root. We just we take square on both sides, from this equation here. So squaring both sides. So you got d squared on the left side, and then when you square the radical, so the index here, which is 1/2, you square, so 1/2 times 2, so this becomes 1, so we have x squared plus y squared. So differentiating both sides implicitly with respect to x, holding y as constant, so we get this result. So this 2d times the derivative of d with respect to x equal to 2x, because y here is constant, right? So we hold y as constant. We hold y as constant. And thus d times partial derivative of d with respect to x equal to x. So we just divide both sides by 2, right? So dividing both sides by 2, so you have this 2 here, 2 divided by 2, right, equal to 1. So 2 divided by 2 equal to 1. So what is left is d times partial derivative of d with respect to x equal to x. And since d is equal to 5 and since d is equal to 5 when x equal to 3 and y equal to 4, so where did we get this one? So from here, when x equal to 3, so 3 squared 9, plus when y is 4, so 4 squared 16, so 9 plus 16 equal to 25, square root of 25 is equal to 5. So that's why we have d equal to 5 here. So it follows that, so when d is equal to 5, it follows that 5, because we have to substitute into this equation. So 5 times partial derivative of d with respect to x when x equal to 3, y equal to 4. So substituting, so we got equal to 3, or partial derivative of d with respect to x equal to uh, 3, y equal to 4. This can also be equal to 3 over 5. Okay, so we can say that d is decreasing at the rate of 3 over 5 units per unit increase in x at the point 3/4. All right, so you might ask, where is this coming from? So what we did is we divide both sides. So we have 5 partial derivative of d with respect to x, okay, equal to 3, right? So dividing both sides by 5. So 5 partial derivative of d with respect to x equal to 3. So divide both sides by 5. So divide this by 5. Divide this by 5. So 5 divided by 5 is equal to 1. Okay, so that's why we have here partial derivative of d with respect to x equal to 3 over 5. So thus d is increasing because our slope here is, because this one is our slope. So our d is increasing at the rate of 3 over 5 units per unit increase in x at the point with coordinates 3 and 4. All right, so this is another example applying our implicit differentiation, partial differentiation. Now you might get bored, no? Because there are a lot of examples already that we have discussed on this topic, partial derivatives. Actually, there are more to discuss, class, but because of the time constraints, we'll just select some of the remaining topics. All right, so the next topic for this one is the partial derivatives and continuity. So I will skip this part. Then I will discuss this briefly, the partial derivatives of function with more than two variables, which we already had discussed partially before, and also what we did in the big blow button. So there was an examples there. Then I will give more emphasis on the higher order partial derivatives, and then I will leave the rest of this topic class. Okay, so see you again in the next video covering these partial derivatives of functions with more than two variables. Just make a little review of what we have done uh, in the use step. No, we have the big blow button recording or video lessons that were recorded during one of our sessions. Okay, thank you very much. See you in the other video. Bye.